So like previous days, if you have any query, please stop me and please tell me whatever you want to know, because I'll be not able to see whether somebody raised the hand or so. In context of spatial model, instead of telling that we are going to plan for spatial regression analysis, in general, we say that we are going to frame or model the spatial dependence. Because from your knowledge or experience regarding the spatial statistics, developing maps, etc., you understood there is some concept of lag in context of spatial analysis. Spatial interactions, spatial lags, these are the terms and terminologies we are considering in context of spatial framework. So naturally, when we are going to discuss something which is a setup where there will be a dependent factor and there will be a series of independent factors, the question is coming whether one space is trying to tell something about another space. So, we call it the spatial dependence framework. But before moving to spatial dependence framework, what is meant by spatial lag, what is meant by spatial error, etc., we have to do some kind of review related to ordinary least square and maximum likelihood estimation technique. Ordinary least square technique is always our starting point, so we cannot do anything leaving this ordinary least square technique. However, in context of large sample, we like to use the maximum likelihood technique rather than least square technique. Therefore, along with the review of ordinary least square, we need some idea about the, at least for the test statistics related to maximum likelihood technique. Somebody is just doing the econometrics, whereas somebody did econometrics long back. Somebody is teaching econometrics, So it is a mixed group. So there will be a lot of overlaps, but from certain point we have to start. And therefore, I am starting with the basic regression framework, and then I'll tell you how this basic regression framework will be modified in context of spatial dependence framework. So let's start with the multiple linear regression model, where we have the dependent variable y. Y has n number of rows, so it is basically a vector. So we have the dependent variable, suppose crime rate. Crime rate is the dependent variable. And this time we are not modeling like, whether crime rate in my locality is a function of crime rate of your locality. We are not putting this matter. Simply, we are telling that crime rate depends on education. Crime rate depends on several factors like, detection, etc. How the police force is active, what is the law and order in a particular place, what is the unemployment rate, etc. So in X variable, we are putting certain factors which are related to, detection of crime, which are related to unemployment, education, etc., etc. Whenever we model something, it is impossible to consider all explanatory variables in the model. And for that matter, there are a set of variables which we somehow cannot accommodate in the regression framework. Joint impact of those variables will be captured by the error term. However, we have to remember U is purely random in nature. We start with a framework where U is a white noise, because otherwise we will be not able to present a classical model. A classical model has several nice properties, and for that matter, we need U should be a white noise. Now, one by one, we are going to point out the regularity conditions which make U a white noise. The first and foremost important factor is we have to start with a model having a correct specification. The correct functional specification of the regression will be our starting point. For example, if there is a nonlinear relation, we have to model the things using the nonlinear structure. If there is a linear relationship among x and y, we have to model it using linear structure. The standard thing is, since in economics we start with the demand and supply equations, and then in the macro we consider national income is a function of these variables, consumption, investment, etc. Every time we consider a linear framework. So linear framework is a good starting point. However, there may be certain context where not x, rather x square or x cube, or both x and x square, these things are affecting y. Think about your cost equation that has a particular shape, S-shaped curve, and naturally it is not a linear relationship. So if we do something related to cost, and this depends on several factors, we need to keep in our mind the structure is not necessarily linear in nature. So, correct functional specification is the starting point for any regression analysis. Then there are several standard assumptions, like expected value of this random error should be zero, which indicates there should not be any systematic bias. In a standard econometrics class, we tell that UI is the random error. So if we consider a scatter, the points indicating X and Y, that kind of scatter, so it is expected that some of the points, if I fit something, fit a line which indicates the average, some of the points will be above that, some of the points will be below that. And ultimately, the things will nullify each other. This is number one. And number two is why we will start keeping some bias in our mind while we are framing the regression analysis. So if we plan for, or if we think on ex ante position before implementation of the regression, why should we think that whenever we are writing a model, there should be a constant error? So if we have that kind of feeling, there should be some constant error, that error should be adjusted with the intercept term. So, in general, it is expected that the mean error, there should be a random error. However, the mean of that random error, that should be equal to zero. The second assumption or regularity condition is expectation of ui square is equal to sigma square, which is indicating a constant error variance. To begin with, we are not considering the variance will have a particular shape or ui squared will be related to explanatory variables. So we are not considering any kind of systematic finding in context of regression model. If we expect, ui square will be related to the set of explanatory variables, that is the concept of heteroscedasticity. To begin with, we are not considering that thing. We are considering that there is a constant variance. The third assumption in a classical framework is there should be non-autocorrelation. There will be no association between the errors of two contexts. Expectation of ui uj will be absolutely equal to zero. There is no error correlation. including no spatial autocorrelation. Already we discussed about spatial autocorrelation. So when we are telling about or considering two ui and uj, here we are not considering any kind of spatial autocorrelation. Now, essentially, we are starting with a linear setup. In a linear setup, there should not be any association between the variables which we are considering in the right hand side. So we start with covariance between x and u should be equal to 0. Otherwise, the linearity structure will be questioned. If there is some functional association between the set of explanatory variables and the random error term, in that case, the linearity context will be questioned. Similarly, later we will talk about the fact that we are also not allowing any kind of linear relationship among the explanatory variables too. If I consider y to be the crime rate, and in our x variable we have education related factor or unemployment related factor, or any variable related to law, order, etc., we are starting with the view that there is no association or a very low association between these explanatory variables. So among the right hand side factors, we are not considering any kind of association. Finally, we assume error follows a normal distribution with expectation of ui is equal to 0, and the variance covariance matrix, that is sigma square I. If we just write down the variance covariance matrix here, variance of ui itself will provide the variance covariance matrix. That variance, in this variance covariance matrix, we will have this sigma square constant variance by the assumption of homoscedasticity, and all the off diagonal terms will be equal to 0. So what we can do, we can take sigma square common, and then this matrix reduces to 1 1, and these off diagonal elements will be all 0. So this can be written as sigma square I. So this kind of variance covariance structure, which indicates the assumptions of homoscedasticity along with non-autocorrelation, we are considering that kind of thing. So if these regularity conditions hold, or these particular set of assumptions hold, we call a model a classical one. And since we are considering a linear structure, this is classical linear regression model. Once we frame the model and all these assumptions hold good, in the next step, we go for estimation and the inference. Everybody has some background related to econometrics. Some people are doing during this time. Some people already did this thing. So those who are doing now, after a few classes or so in your regular course, you will find that the beta hat is estimated. Beta hat is the regression coefficient, and that is presented as x prime x inverse x prime y. And we can show that these are all OLS estimators, beta hat OLS. I'm talking about x prime x inverse x prime y. And if we consider the two variable framework, maybe some of you are more familiar with the two variable framework. Can you tell me what will be the formula in a two variable framework? Anybody? What will be the denominator?
Summation yi.
Summation yi square. No. Summation xi square. Summation xi yi. divided by summation xi square. In the in this beta hat, we are getting reflection of the same. In the numerator, we are telling that we will have summation xi yi. Look, here we have x prime y. In the denominator, we are telling that we will have sum of squares of xi. And in context of matrix algebra, to indicate a denominator, we consider inverse. So we are getting the same formula using a number of x's. So it is x prime x inverse, x prime y. Everything in bold in my analysis is indicating matrix. This beta hat OLS is an unbiased estimator, and that unbiasedness we can capture by writing expectation of beta hat is equal to beta. Beta hat is not equal to beta. However, the mean value of beta hat, expected value of beta hat, that is equal to the actual value of the regression coefficient beta. We can also derive the variance covariance matrix of beta hat, and that will have the formula sigma square x prime x inverse. Those who are familiar with the two variable analysis, variance of beta hat is sigma square divided by summation xi square. So when we are writing it in terms of matrix algebra, it is becoming sigma square x prime x inverse. Under most of the circumstances, we have no knowledge about sigma square. And we need to replace this sigma square by its unbiased estimator if it is a finite sample. Now, if it is a finite sample, the unbiased estimator of sigma square is the a square, and this a square is nothing but RSS divided by n minus k, which is the indication of degrees of freedom. I think everybody has knowledge about E, small e, which we denote by residual. So can anybody tell me what is the difference between error and the residual? What is the difference between U, with which we started, and the E here we are writing, we are telling the residual. Anyone, please go ahead.
Ma'am, error cannot be observed, so we use residual.
Yeah, and what formula for error and what is the formula for residual? Anybody?
So error is essentially the difference between the observed value and the true value, while residual is the difference between the observed value and the estimated value.
Very good. So EI is the YI minus YI hat. Okay. So this true Y is not in front of us. What, suppose we are making any demand analysis. What is the true demand for orange? We don't know. We can collect the observations which we call the sample observations. So population Y is unknown. We can identify only the observations in a sample. So these is the set of observed values. This is the actual value. So what we do on the basis of these observations, we can find out an estimated value of Y. This EI is basically observed minus estimated, and therefore this EI or the residual can be realized. EY cannot be realized because of the presence of the true value of Y or the population value of Y. EI is realized because it is actually we are observing regarding the demand for orange against different prices or different incomes, etc. And YI hat is the estimated value. Very good. Since we are discussing the finite sample as well as large sample simultaneously, here I should mention that if I apply the maximum likelihood estimation technique instead of ordinary least square technique, the estimated value of beta hat will remain unchanged. We are using different formulation. However, ultimately, the beta hat OLS and beta hat ML values will be similar. There will be some difference if I consider or if I estimate sigma square. If it is the least square based thing, it will be RSS, residual sum of squares. By the way, the residual sum of square E transpose E is nothing but summation EI square, residual sum of squares. In context of maximum likelihood, this estimator will change a bit. In the denominator, instead of degrees of freedom, we are getting the total number of observations. I repeated, there is some method if the sample is finite, there is some other method if the sample is large. Now, at this point, we need to understand what is the difference between a finite sample and a large sample. Finite sample is a sample which does not have any limiting property. Large sample is a sample where there is a limiting property. If the size of the sample moves towards the population, if I consider sample to be small n and population to be capital N, if it is like this, or we can say, since the population can be infinite, if I say that the sample is moving towards infinity in the limiting sense, in that case, we will consider our sampling context as the large sample context. So if the sample size is large, the number of observations are so large, there is no need to take difference from the number of parameters to be estimated, which is defined by K. So, if something is moving towards population or infinity, it doesn't matter whether we are subtracting the number of parameters to be estimated from this or not. Always there will be sufficient degrees of freedom. However, in context of finite sample, it is really important to understand what is the number of observations, that is, what is the sample size and how many parameters we are going to estimate. The difference between the two is known as degrees of freedom, as I think all of you know. In case of large sample, instead of considering unbiased estimator of sigma square, we will consider whether the estimator is consistent or not. Now, when we are finding some estimated value, we are finding the estimated variance of beta hat, because under most of the circumstances, as we are understanding, since we don't know sigma square, actually we will be not able to calculate var beta hat. Rather, we will be able to calculate var beta hat of this. That is the estimated value of variance of beta hat. We have these things in our hand. However, as you know, as long as we can't prove whether the estimated value is statistically significant or not, there is no acceptability of this estimator. At the end of the day, we need that this estimated value should be statistically significant. Thus, we frame our null hypothesis in the way as it has been presented here. The null hypothesis is beta I is equal to 0. That is, beta 1 is equal to 0, beta 2 is equal to 0, etc. So if we have k minus 1 number of parameters, beta, in any regression analysis, if I consider 3 explanatory variables, there will be 3 betas, 5 explanatory variables, there will be 5 betas, etc. So individually, we are assuming these beta values are equal to 0. Now, if this null hypothesis is accepted, in that case, a particular x has no role in explaining the variation in y. You will be able to estimate the parameter. However, this parameter is not effective just because of the fact that it is statistically insignificant. Generally, we run this kind of test using the t statistic, where t is nothing but the estimated value of beta divided by standard error of that estimated value. So if I have three explanatory variables, x1, x2, and x3, and we set this hypothesis beta 1 is equal to 0, beta 2 is equal to 0, and beta 3 is equal to 0, three times I have to estimate this t value, beta 1 hat divided by standard error of beta 1 hat, and so on. I think you are familiar with the level of significance, etc., this kind of concept. So once we get this particular value, we need to compare it with the tabular value to check whether the estimated value is crossing the tabular value or not. If the estimated value crosses the tabular value, in that case, we will reject H naught. Otherwise, we have to accept H naught. Since we are doing something which is applied in nature, we actually don't depend on the table, and we will not check the estimated value against the tabular value. Rather, our focus will be on p value. P value. Now, what is p? Already we discussed in context of autocorrelation. P is the probability of type 1 error. Now, in context of inference, what we do, there are null hypothesis as well as alternative hypothesis. So there are four possible contexts. Null hypothesis is true and accepted. Null hypothesis is true but rejected. Alternative hypothesis is true and accepted. Alternative hypothesis is true but rejected. So all these four possibilities appear. Among these, two possibilities are correct decision. If the null hypothesis is true and accepted, it is good. If the alternative hypothesis is true and that is accepted, that is the null hypothesis is rejected, then that is also a correct decision. But when the null hypothesis is true but rejected, that is the probability of type 1 error. And if the null hypothesis is false but accepted, in that case, we are committing type 2 error. So p-value, in context of inference, we cannot minimize both the probabilities of type 1 error and type 2 error simultaneously. So we fix the probability of type 1 error at a particular level, and subject to this, we minimize probability of type 2 error. Instead of minimizing probability of type 2 error, we can also maximize 1 minus probability of type 2 error. So this 1 minus probability of type 2 error is known as power of the test. So these things we do in the basic statistics class. However, these are extremely important because every time what is p-value, why we are fixing it at 5%, 1%, these questions come. So, what I told, we actually want to minimize probabilities of both the errors. However, we can't do it simultaneously. Therefore, we fix the probability of type 1 error conventionally and minimize the probability of type 2 error. Now, when we are keeping probability of type 1 error at a small level, conventionally we do it at 5% or 1% level. So there is 5% chance that the null hypothesis is true but has been rejected, or there can be 1% chance that the null hypothesis is true. However, because of the distributional aspects, it has been rejected. So looking at the p-value, so if the p-value is 0.05, however, greater than 0.01, in that case, we will be able to ensure the probability of type 1 error is very small. It is not exceeding 5%. It is greater than 0.01. So it is greater than 1%, however, less than equal to 5%. If this is the context, in that case, we consider a coefficient to be statistically significant at 5% level. If, this p-value is 0.01 or less, in that case, we reject the null hypothesis at 1% level, or we consider the coefficient is significant at 1% level of significance. So the concept of test statistic and parallelly p-value, these will tell us whether a coefficient is statistically significant or not, and if it is significant, whether it is significant at 5% level, 1% level, and so on. Along with checking the significance of individual level coefficients, we also need to check whether the model is overall significant or not. To check or to test whether the model is overall significant or not, we have to set a null hypothesis where, apart from the intercept term, all the regression coefficients will be there. So look at the null hypothesis to check the joint significance. So it is beta 2 is equal to beta 3 is equal to up to beta k is equal to 0. So apart from beta 1, which is indicating the intercept term, we are setting all the coefficients simultaneously equal to 0. So actually, x's cannot explain why. The y value is a constant, and that is given by the intercept term. So this is the idea. In this context, we discuss about two phrases. One is the restricted model, another is unrestricted model. Unrestricted model is the model where we have all explanatory variables, the original model. Whereas the restricted model is the model where we are dropping a single coefficient. If, we consider one of the betas, or if I consider beta 1 is equal to beta 2 is equal to 0, but rest of the coefficients are non-zero, in that case, we have to drop x1 and x2, the variables associated with those coefficients. Whatever we do, and for these particular joint significance, we are dropping all the explanatory variables together. So whatever we are getting after implementing the null hypothesis is known as restricted regression model. So now, after implementation of null hypothesis, we have a new regression equation. We have a new equation, which we are calling the restricted equation. Now for the old one, which is the unrestricted equation, where we didn't implement the null hypothesis, we will be able to calculate residual sum of squares, because for every regression, we will be able to calculate what is total sum of squares, what is explained sum of squares, what is residual sum of squares. Residual sum of squares is nothing but summation ei square in terms of matrix algebra E transpose E. So separately, for each of the equations, you will be able to calculate residual sum of squares. So using the residual sum of squares of the unrestricted model, which we are calling URSS, unrestricted RSS, and residual sum of squares of the restricted model, we can frame one F statistic. This is RRSS minus URSS divided by K minus 1. The whole thing divided by URSS divided by the degrees of freedom of URSS, which is given by N minus K. In the numerator, the K minus 1 we have written, that is nothing but the difference between the degrees of freedom of these two elements. Okay, so for RRSS, we have a relevant degrees of freedom. For URSS, we have a relevant degrees of freedom. So if I take the difference between the degrees of freedom, we are getting this K minus 1. So anybody Please help me to find the degrees of freedom of RRSS and URSS. Would anybody, we are beginning with, say, this is the equation with which we are starting. For URSS, I hope you are understanding the degrees of freedom will be n minus k. This one. df n minus k. What will be the degrees of freedom for this? Anybody? This we should write as, because this time we have k minus 1 number of explanatory variables. So we can write the matter in this way too. What will be the degrees of freedom of RRSS? What is the number of explanatory variables in the restricted model? Anyone? What is the number of, we are setting beta 2 to beta k is equal to 0.
Only
So what is the number of explanatory variables in the restricted model?
ma'am, there are no explanatory variables.
There are no explanatory variables. So what will be the degrees of freedom? N minus 0? Isn't it?
Yes, ma'am.
So the degrees of freedom will be n minus 0, which is simply n. Then, we are considering degrees of freedom of restricted RSS minus n plus k minus 1. Okay. So we are getting k minus 1. So this k minus 1 is nothing but the difference between the degrees of freedom of the terms we have written. Another idea is this is nothing but number of restrictions. So look, what is the number of restrictions? We are starting from beta 2 and moving up to beta k. So we have k minus 1 number of restrictions. That's all. So in this way, we define this thing. There are some more things as well. Now this residual sum of squares, this follow chi-square distribution. RSS is anyhow summation EI square. All RSS is following this formula. Okay, so this summation EI square is basically the sum of squared of standard normal variates. So this follows chi-square distribution with relevant degrees of freedom. The difference between two RSS that will also follow chi-square distribution. In the numerator, we have a chi-square distribution deflated by relevant degrees of freedom. In the denominator, again, we have chi-square distribution with the relevant degrees of freedom. So when this is the composition, we get a ratio between two chi-squares deflated by their relevant degrees of freedom, chi-square divided by k minus 1, chi-square divided by n minus k. This will follow F distribution. So remember that EI square, summation EI square or E transpose E, that follows chi-square distribution because this is the sum of squares of standard normal variates. So since these are following chi-square distribution, the ratio will provide us the F distribution. Why I am telling all these things? Because now we are moving towards the maximum likelihood part, and you will find that the test statistics are changing a bit. However, always the things will be in between tau, which is the standard normal distribution, t, student's t distribution, chi-square, or f. Okay, so we should have a very clear idea about what is a standard normal distribution, how we are getting t from a standard normal, how we are getting chi-square from the standard normal, and how we are getting finally the F distribution again from standard normal distribution. So standard normal is the parent distribution, or you can say the normal is the parent distribution, and all these tau, chi-square, t, f, these are the derived distributions after adjusting the basic normal distribution. I already mentioned the value of the estimated coefficients will not differ between the least square and the ALS technique. However, I mentioned how the estimated variance, or in other words, the standard error value is varying between the two methods. Similar thing will happen when we are going to check whether our regression coefficients are statistically significant or not. Here, the test statistics we generally use all are related to large sample. There are three types of test statistics. One is the likelihood ratio test, the second one is the Wald test, and the third one is the Lagrange multiplier test. All the test statistics are based on the mechanism of there will be a restricted model, there will be unrestricted model. When we are talking about the restricted model, it is not necessary that all the coefficients will be null in the null hypothesis. Some of the coefficients we can consider zero, some of the coefficients we can consider non-zero. So it can be a mixed and match. However, while we are implementing the null hypothesis, we are getting a restricted model. While we are keeping the model intact, that is known as unrestricted model. So if you look at the likelihood ratio formula, which we generally define by lambda, it will be ratio of two likelihood estimators. The numerator is a function of L for likelihood. Numerator is a function of beta tilde and sigma tilde squares. What are these beta tilde, sigma tilde? Look at this. Restricted maximum likelihood function with the residual E star. We are defining the residual of the restricted model by E star, E subscript star. So this L is coming from the restricted model. L beta hat sigma hat square, the denominator maximum likelihood function, is related to the unrestricted model. So in the numerator, we are keeping the L estimated on the basis of restrictions or restricted model. in the denominator, we are keeping the likelihood function related to unrestricted model. The idea is, if these two things are very close, that is, if lambda moves towards 1, in that case, you are putting restrictions, however, that is not providing any significant impact on explanatory capacity of the model. You started with 5 variables, then you are dropping 2. However, the likelihood function you are getting from the 3 variable context and the 5 variable context, if these are very close to each other, in that case, actually the x's you dropped do not have any significant capacity to explain y. So this is the logic in framing this kind of likelihood ratio. It has been proved by the statisticians, -2 of log of lambda, that follows a statistical distribution. So this is the logic by which we can arrange the factors. However, directly lambda is not following any distribution. So we need to make some adjustment, scale change. And after changing the scale, it will follow the chi-square distribution. And if you look at the formula, it is looking a bit complicated. However, there is nothing except the fact that it is RRSS minus URSS divided by RRSS. Here, 2 RRSS minus URSS divided by RRSS. In standard F statistic, which we use in context of least square technique, in the denominator, we keep URSS. That is the difference we measure between restricted RSS and the unrestricted RSS, that we measure with respect to the RSS of the original model. So we consider the ratio in that way. However, in the likelihood ratio test, instead of considering the original RSS in the denominator, we consider the restricted RSS in the denominator. The Wald test, that is also very, very similar to that of the F statistic. Here RRSS minus URSS divided by URSS kind of thing we are considering. However, this ratio will be multiplied with n. The formula for Lagrange multiplier test, it is very similar to that of Wald, only in the denominator, instead of considering URSS, this time we are considering RRSS. So we are playing the game around the same numbers. We are rearranging our RRSS, URSS, and defining certain test statistics. So all these test statistics have the same role as T, F kind of thing, So they will tell us whether we will reject H naught or we will accept H naught. Rejection of H naught indicates X has significant capacity to explain Y. Acceptance of null hypothesis indicates X cannot explain Y. Once we complete this business, yes, the coefficients are statistically significant, or we can find out these are the coefficients are statistically significant, while these are the factors which cannot explain Y in a significant way. In the next step, we talk about measurement of the goodness of fit. If it is the least square based technique, you are familiar with multiple R square and adjusted multiple R square. R square is ESS by TSS, which is quite a natural measure of goodness of fit. ESS is the explained part, TSS is the total variation in YI. So we are measuring a proportion, how much of the total variance, total variability of YI can be captured using the set of explanatory variables. So ESS by TSS is a very natural measure of goodness of fit. And that ESS by TSS we can present in this way too. We, instead of writing ESS, we can write the numerator as TSS minus RSS divided by TSS, which is giving us 1 minus RSS by TSS. Now, R square, it is a typical measure, you know, where we are basically considering ESS with respect to TSS. Now, if you incorporate one explanatory variable, one more explanatory variable in your regression analysis, always explained sum of squares will improve. It doesn't matter whether the coefficient is at all significant associated to that x or not. So whenever you are adding one more explanatory variable in your analysis, ESS is improving, and thereby ESS by TSS, that is also improving. So the question becomes, how long you will continue to incorporate new explanatory variable in your analysis. Why this question is appearing? There is a concept of goodness of fit in least square analysis, which is measured by n minus k. This is the gap between the number of observations you are considering and the number of parameters you need to estimate. Lesser the gap, weaker the position. A regression will be a good regression if there is a sufficient gap between n and k. So if you increase indefinitely the number of explanatory variable to improve your R square, which is the measure of goodness of fit, that will indefinitely reduce n minus k given a fixed number of observations while you are discussing the story. Okay, so this in turn indicates the degrees of freedom will continuously fall, and that is not a good thing for any regression analysis. So we have to make a trade-off. We have to keep sufficient degrees of freedom. At the same time, we have to keep our ESS with respect to TSS at a certain level. So we bring the concept of adjusted R square, where we deflate RSS and TSS in the earlier formula, or ESS and TSS in the earlier formula, by their respective degrees of freedom. As we bring the degrees of freedom in the formula, it will take care of both the aspects. That is, as we are bringing one new explanatory variable in our analysis, our goodness of fit is improving. At the same time, there will be a cost too, that is reduction in the degrees of freedom. So this formula will make an adjustment and will help us to optimize the situation. In context of maximum likelihood, the information is a little bit different. We get the AIC and SWOG criterion. In fact, BIC is also there, Bayesian Information Criterion. Since I am not doing something which is related to Bayesian context, therefore I didn't keep that Bayesian information here. So the other two relevant information is the Akaike Information Criterion and SWOG Information Criterion. Now, if you look at the structure of the formula, here, we are considering 1 minus RSS by TSS. Here, we are considering log of RSS by n, plus k by n, log of n. Here, too, we are considering log of RSS by n. So there is some kind of link between the type of formula we have considered. So RSS is coming every time. At the same time, remember the aspect that since R square is based on ESS by TSS, higher the value, better the position. Whereas in case of Akaike and the SWOG criterion, these are based on RSS in the numerator. So lesser the value, better the context. So the logic for two types of measures of goodness of fits are reverse. For OLS based measure of goodness of fit, higher the value, better the situation. As the value moves towards 1, we are happy. However, for Akaike and SWOG criterion, or these kind of large sample based criterion, lower the value, we are more happy. After discussing these things, we move towards the regression diagnostics. We start with the concept of multicollinearity. Multicollinearity indicates, there is some kind of linear association between the columns of the X matrix. In other words, there is some kind of overlap between the explanatory variables we are considering. Again, suppose we are considering the crime rate, and suppose we are keep considering both law and order, as well as whether there is nearby police station, whether the number of uh, persons who are maintaining law and order, that is very high. So if we bring all these aspects, there may be certain kind of overlaps between the variables. And if there is certain kind of overlap or value wise, if one column generates other column, in that case, there will be the context which is known as multicollinearity. As I mentioned, for a linear regression setup, we don't want that there will be some kind of functional association between the right hand side factors. So, naturally, we don't want that there will be some kind of association between the set of explanatory variables we have. So, we need some mechanism to understand whether our model is suffering from multicollinearity or not. There are two factors by which we can somehow can say that there is an indication of multi.
Ma'am, you were inaudible. Sorry to interrupt. You were actually inaudible.
Okay, let me check. Hello, I'm audible now.
Yes, ma'am.
Who told that I am not audible?
Now you are audible, ma'am.
Okay, so would
For
you
a bit,
please
you
check?
were inaudible.
Uh, Anybody help us whether I was really not audible, or it is the problem related to some students because of their connectivity.
Ma'am, we could hear you.
Okay, so Moyuk or others, please check your connection. Maybe there is certain issue related to your connection. So this is the problem with the online things. So here I am mentioning about the condition number and the variance inflation factor. Condition number is not a test. It is some kind of indication of potential problem. So when I'll show you the regression output, you will find that using geoda or geoda space, we are getting information related to condition number. So if the condition number is excessive, it exceeds the value of 30, some literature is telling 50, in that case, it is giving some indication of multicollinearity. Another detection mechanism is the variance inflation factor. Those who are doing research, doing PhD or some kind of research, you will find that a variance inflation factor is we discuss more about this variance inflation factor because most of the software give information about variance inflation factor. Okay, so a variance inflation factor uses this kind of formula 1 by 1 minus RH square, where RH square is the multiple correlation among the X variables. Here K is the order, among the X variables, among the explanatory variables. Okay, just a minute. I have to take a call. Sorry. So, RH square is the multiple correlation among the X variables. So, and this time we are not considering any correlation matrix where we are involving all X variables along with Y. Here, we are keeping our analysis restricted among the X variables only. So, if there is high correlation R square H, that is also an indication of multicollinearity, and variance inflation factor. Actually, in context of multicollinearity, those who went through the aspects of detection of multicollinearity have some idea. In that case, the variance of the estimated coefficients start becoming very high. Okay, so variance inflation factor, and if we start doing the deriving the formula, we can derive this factor is basically inflating the variance. So in presence of multicollinearity, it happens that variance of the regression coefficients start becoming high. One of the ways by which we present multicollinearity is that overall the model is significant, that is, F statistic is very high. However, all the individual based T statistics start becoming very small. Okay, the reason is standard error of beta hat starts becoming high. So T statistic, which is beta hat divided by standard error of beta hat, that starts falling. So, in presence of the same thing can be presented in different ways. So one way, F is very high, T statistics are very small. Another thing is estimated variance of the regression coefficients start becoming very high in presence of multicollinearity. Same thing we are telling from different angles. So we can find out actually the variance the variance can be inflated by a factor 1 by 1 minus RH squared, where RH squared is the multiple correlation among the explanatory variables. So this VIF standard is it should be less than 10. If it is less than 10, in that case, the multicollinearity or the association among the X variables, that is tolerable. However, if it crosses the value 10, in that case, we will be not able to tolerate that much association among the X variables. In this context, I like to add a note. Multicollinearity is a bit tricky problem. In context of multiple regression analysis, when we are trying to frame any model, it is really, really difficult to plan for X variables which will be truly orthogonal in nature or which will be truly independent from each other. There will be, certain level of association among these variables. Otherwise, why? To frame the demand, we are bringing a set of variables: price, income, gender, education, because we feel that, our chemistry between these factors, taste and preference, price of the commodity, income of the consumer, gender, education, household size, these things together frame the demand for a particular commodity. Similarly, when we consider the supply equations, it is not that we put anything and everything. We put several things, keeping in our mind, the chemistry between these factors will finally result in supply. So always, when we are selecting a particular set of variables, there is rationale behind it. So there can be a certain degree of association among the variables. Therefore, it is not like, homoscedasticity, heteroscedasticity, or biased, unbiased error terms. Autocorrelated, non-autocorrelated. It is not like this. It is not binary. Some degree of multicollinearity will be always there. The thing is, whether it is above the tolerance level or below the tolerance level. If it is below a level, say 10, in terms of variance inflation factor, in that case, we can tolerate the presence of multicollinearity. The next is checking the normality assumption. We generally do it in the Jerk-Bera test statistic.
Excuse
Yes.
me. Ma'am.
Yes.
Ma'am, is the presentation visible to the others? Means I am not getting the presentation.
Okay, so,
Presentation is not visible.
okay, sorry. Why didn't you tell me? Is it okay now?
Yes, ma'am.
Okay, so here is the measure of multicollinearity, condition number, and variance inflation factor. Next, we are considering the statistic by which we can check the normality assumption, whether the distribution is normal or not, because the last regularity condition is the random error is following the normal distribution. So Jerk-Bera statistic is based on skewness and kurtosis of the distribution. Actually, looking at the skewness and kurtosis, we understand whether the distribution is leptokurtic, mesokurtic, or platykurtic, okay, or the distribution is positively skewed, symmetric, negatively skewed. So all this information related to kurtosis and skewness tell us whether the distribution is normal or not. For a normal distribution, what will be the nature of skewness and kurtosis? Anybody? Please go ahead. Anybody. What will be the nature of skewness and kurtosis in context of a normal distribution?
Curtises will be 3, ma'am.
In terms of,
Mesocortic. Mesocortic.
Mesocortic.
Yes.
Yes.
And in terms of skewness,
It will not be skewed. Means it will be like
symmetric.
symmetric. Yes.
Symmetric around the mean. Symmetric around the mean. Okay, so if this is the mean, mu say, sorry, this is the shape of a normal distribution, bell-shaped curve. The left-hand side part, the right-hand side part will be similar. So if some distribution is symmetric around the mean, that distribution will be considered as the normal distribution. Jerk-Bera or JB statistic is based on B1 and B2, where B1 is the measure of skewness. This is the moment measure of skewness. And B2 is the measure of kurtosis. This is also the moment-based measure on kurtosis. Okay. For the Jerk-Bera test, the null hypothesis is that data is normally distributed. Okay. Now, for the rest of the test, generally we consider zero parameter or no type of hypothesis. For example, when we are trying to test the significance of the coefficient, we are setting null hypothesis as the coefficient is not significant, 0. When we will go for testing heteroscedasticity or autocorrelation, we will start with the null hypothesis stating that there is no heteroscedasticity, there is no autocorrelation. So no type of hypothesis or zero parameter type hypothesis we consider in general in context of regression and its diagnostics framework. However, the Jerk-Bera null hypothesis is a little bit different. It is considering the normality in the null hypothesis, and it will be tested against the distribution is not normal. Next, we consider heteroscedasticity. What is heteroscedasticity? Heteroscedasticity is indicated by the residuals are somehow related to the set of explanatory variables. If residuals are not related to the set of explanatory variables, in that case, we consider the context as homoscedasticity. However, if there is some kind of association between xi's and ei's, it can be ei and xi square, it can be ei squared and xi, or if there are say three explanatory variables, we can consider x1 square, x2 square, x3 square. They are cross products like x1, x2, x2, x3, etc., depending on whether we are considering Drush-Pagan Lagrange multiplier test or we are considering White test, etc. So formula will change. However, most of the formulas center around some kind of relationship between the residual and the x terms. Only for several formula, instead of using x, they use y because they tell that y is capturing the joint impact of x's. But standard is some kind of association between ei and xi we consider while we prepare the formula for the test statistics related to detection of heteroscedasticity. So these are the three, types of tests which we use, in context of our analysis. In fact, the software we are going to use, that software will report heteroscedasticity on the basis of these tests only. There are several other tests as well. So here is the example of White test. If we start with two explanatory variables in the White test, at the end of the day, the test statistic will be based on a new regression where RSS, Ui hat is equivalent to EI, Ui hat will be regressed on X2i, X3i, that is the explanatory variables, their squares, their cross product, etc. So take in a standard econometrics book, whatever detection mechanisms you will get there, those things will be based on some kind of relation between residual and the explanatory variables. Now, in context of this kind of heteroscedasticity or autocorrelation, in case of autocorrelation, as you know, we consider the association between the error terms. If we plan for how to estimate the regression coefficients, instead of using OLS, we generally go for generalized least square technique. So I want to say, if I have spherical variance covariance matrix. What is spherical variance covariance matrix? A variance covariance matrix having both the heteroscedasticity and autocorrelation. So if my diagonal elements change continuously, so let me use the boat, So if variance of beta hat, which is indicating the variance covariance matrix, sigma 1 square, sigma 2 square. And here too, we have elements, non-zero elements. If this is the context, we call this matrix a spherical variance covariance matrix. Okay, or A matrix where, better to say, there is both heteroscedasticity and autocorrelation. In this context, we present this by omega. Omega is the factor by which we generally present this kind of variance covariance matrix. So in context of presence of heteroscedasticity and or autocorrelation, instead of using ordinary least square technique, we use generalized least square technique to get unbiased as well as consistent minimum variance as well as efficient estimators of beta hat. So expectation of u prime we are presenting by sigma square, omega, and this omega is not equal to or in any way equivalent to sigma square I. So variance of beta hat in that case is presented by x prime x inverse, x prime omega x prime x inverse. Okay. So this will be the formula for variance of beta hat in presence of this kind of problem of heteroscedasticity and autocorrelation. What was the formula for variance of beta hat when we didn't have this kind of issue? Sigma square x prime x inverse. Look at this. Sigma square x prime x inverse. However, when there is heteroscedasticity along with autocorrelation, this measure changes to this. Actually, what happens in the variance of beta hat formula, if omega is sigma square I, so let me write it down in this way. This is the formula when we have homoscedasticity along with the non-autocorrelation. So what we can do, this sigma square is a constant. So I can keep it outside the range of the entire thing. So sigma square, then x prime x inverse, x prime x prime x inverse. I is the identity matrix. So if it is multiplied with x, it will remain unchanged. So these two things will be adjusted. At the end, we will get this formula as the variance of beta hat. Here, the thing will not be adjusted. So the formula has this x prime omega x. So that's the idea. Okay, so look at this slide, I am coming within a minute. Is the slide visible perfectly?
Yes, ma'am.
Okay. I'll not spend much time over this. I'll send you the slide, so that, in fact, in the recording also you will get this thing. However, just look at one thing, uh, while the individual elements in the matrix omega cannot be estimated separately, White suggests a consistent estimator of V, which is x prime omega x, this part. White is suggesting instead of using x prime omega x, we can use 1 by n x prime sx. What is the problem with this omega? There will be sigma 1 square, sigma 2 square, etc. The off diagonal element, that is the covariance between two errors. These things based on sigma, that is the population variance, are unknown to us. So omega we can define theoretically. However, the elements of omega consists of are dependent on population variances. That is the problem. So each of the factors we will be not able to adjust with some estimated value. Rather, we can consider one sample based variance covariance for the error term u, which is given by 1 upon n x prime sx. So x prime omega x is the variance covariance of the error term that can be adjusted by this particular estimated factor. If we do this and present variance of beta hat as hat of variance of beta hat, that is the estimated value of variance of beta hat, the formula is becoming x prime x inverse, pre-multiplication, post-multiplication, same as before. However, x prime omega x has been replaced by x prime sx. If variance of beta hat is calculated following this formula, we call it robust standard errors. So many of you are familiar with the term robust standard errors in presence of heteroscedasticity, or if we suspect there will be heteroscedasticity, autocorrelation, we estimate the robust standard errors. So this is the meaning of robust standard errors. Now there is a particular transformation of the formula given by Kelejian and Prunch in 2007. So this is the White's formula. So later you will get some of the adjustments in this formula. The basic logic is same. However, they presented variance of beta hat using a little bit different formulation. Among these, Kelejian and Pracha, I am mentioning here because the software we are going to use that will use this particular statistic as well to provide the robust standard errors. So look at the formula. Main essence is, if there is heteroscedasticity, autocorrelation, one of the two simultaneously, both, we will shift for robust standard error measures. Now with this background, now we are moving towards a little bit different context where there is the spatial component. So now, if we bring the space in our analysis, we can frame spatial lag model and the spatial error model, which have some similarity with the standard OLS framework, and of course, there will be some dissimilarity as well. Now, simply diagrammatically, if we like to present the ordinary least square context, I am considering crime rate in my locality and crime rate in your locality. Crime rate in my locality in the standard context is a function of explanatory variables of my locality only. Crime rate in your locality is a function of explanatory variables, as you know, in your locality. So what I am telling, in our model, crime rate depends on proportion of educated individuals, or say proportion of individual, percentage of individuals having higher secondary or higher level of education. We expect that higher the proportion of educated individual in a locality, lesser will be the crime rate. Okay, lesser the unemployment rate, better will be the context in terms of crime, lesser will be the crime. So we have some idea, some expectations regarding the signs of the variables we are considering. If the law and order, discipline, number of persons in local thana or like that, that is quite better. In that case, we may expect the crime rate will be lower in that locality. So I am considering the local crime, and we are assuming that local crime is a function of several explanatory variables which we need to collect on or for that locality only. And for my neighboring locality, we have to do the same. So we are not expecting any influence from the neighbors. We are not considering crime rate in my area is function of crime rate in your area, because we are not assuming the context that education in your locality, unemployment in your locality may affect the crime rate in my locality. So that kind of spillover in terms of space is absent in context of a classical linear regression model. However, in reality, it may happen that yj is function of both xi and xj. Again, yi is a function of both xi and xj. So crime rate in a particular locality may be a function of number of individuals having higher secondary or higher level of education, not only in that locality, but also in neighboring locality. Unemployment in not only in that locality, but also unemployment rate in the neighboring locality. In reality, this happens because, those who are involved in crime, they are not concentrated in a particular location. Okay, generally they will not go for any kind of crime in their locality, rather they will go to some other places. So this happens, many a times, the employment rate in a particular locality, education in a particular locality, health related behavior in a particular locality, these are functions of what neighbors or neighboring localities are doing. Sometimes you may simply copy the neighboring households, or sometimes, there is some explanatory variables which are related across the localities. So if this happens, this yi and yj will be interrelated, or we can say that yi is a function of neighboring y's. If this is the context, we call the context as there is spatial dependence through spatial lags. Any question? So look at this point. In the spatial lag model, the dependent variable y in place I is affected by the independent variables in both place I and j. Another variant is the spatial error model. Now, what is error? As discussed, it is the combination of the factors which may influence y, but we could not incorporate those variables explicitly in the regression framework. So error is the component, which is the joint impact of explanatory variables which we could not incorporate in the regression analysis. So explicitly, the excess we considered in our model building exercise, those excess are not interrelated. However, some of the factors which we could not incorporate in our model, among those factors there are interrelation, and for that matter, two y's are related to each other. So if the channel is the random error component of the different localities, which is ultimately result in some connection between neighbor and the concerned locality, we call it the spatial error model. So if there is interrelation among x variables or x in a particular locality as well as x in the neighboring locality have impact on y on the concerned locality, we call it a lag model, as if, yt is a function of yt minus 1, this kind of lag. Yi is a function of yj. So we are calling it spatial lag model, and this is appearing via the x channel. Another possibility is that there is interconnection among the errors because whatever left out variables are there, there is some kind of connection between across the localities, and for that matter, there is some spatial component captured in the error term. Now the thing is how the basic classical linear regression model will be revised under the context of spatial lag and under the context of spatial error structure. So let's start with the spatial lag model. In our particular example, the data set we used in context of autocorrelation, we have the information related to child malnutrition, P waste, proportion of child wasted, that kind of information we used that information in our analysis. There is information regarding the age of marriage. We created a variable called child marriage, whether an individual faced child marriage or not, So that kind of variable is there, and we already handled that kind of variable. So let's consider that particular data set where we have, some variables with the help of which we can frame a regression. So it is possible that child malnutrition in neighboring districts affect malnutrition in the concerned district. We are trying to establish the lag in terms of the y variable. Y is the malnutrition. Malnutrition or proportion of child facing wasting between the neighboring locations have a kind of interconnection. So that kind of thing we are going to describe using this model. So, the model we will write as y is equal to rho w y plus x beta plus u. So far, we learned about y is equal to x beta plus u. The new component we are bringing, that is this rho wy. Now think about a time series model with which we are more familiar. Yt is equal to rho yt minus 1. This is the autoregressive framework plus x beta plus error. Suppose we are considering this. So here too, we are considering the same. So rho is the coefficient for y in the neighboring district. In a time series model, rho is the coefficient of time lagged variable. So the same type of analysis we are doing. So rho is the coefficient associated with the lagged variable. If it is a time series model, we will consider the lag in terms of time. If it is the cross-section based or this kind of spatial model, we will consider this coefficient related to neighboring y. Now, the concept of neighbor has been captured using the weight matrix W. So in case of time series, we write yt minus 1. Here, to indicate my neighbors, I am considering wy. That is, I am multiplying the y variable of the neighboring parts using the weight matrix W. W is, bridging the gap between, y of the particular locality and y of the neighbors. So W is that particular lagged component. Better to say wy together is indicating y of the neighboring areas. If I consider any kind of social network, my academics depends on academics of my peers. So peers are coming in this way. My grade, and this is the grade of my peers. That is the thing. So wy is the spatially lagged dependent variable with associate autoregressive coefficient rho. Rho is the coefficient, Here, we call this model the autoregressive model because y is regressed on another y. The similar logic we are applying here. Y is regressed on another y. Therefore, it is an autoregressive structure. So rho can be interpreted as autoregressive coefficient. Now, the question is, in this particular framework, why we are expecting that y's will be related to each other, why we are planning or why we are suspecting this kind of spatial interactions. Contextual factors like education level of women, wealth holding, cultural factors like prevalence of child marriage, environmental factors like temperature, aridity, this kind of things, or night light, this kind of things may be very, very similar in neighboring regions. Okay. So for that matter, especially the cultural factors, generally for the culture, we find in the eastern zone, this is the culture. In the western part, this is the culture. In central place like UP and Bihar, this is the culture. In northern districts, this is the culture. In southern districts, this is the culture. We specify culture in that way. We actually break the whole part in several regions, and we say that there is a culture to do this practice. So this generally we always say food habits is similar in these particular zone. Compared to this particular zone, for this particular zone, the year of marriage, the age of marriage is quite high. So we specify the things in that way. So for the cultural factors, generally, the concept is a zonal or spatial concept. So, if I consider the household-wise analysis, or if I consider the district-level analysis, we are expecting there are certain cultural similarity for certain area. So if this is so, in that case, this may affect the Y variable, if we expect there is certain kind of behavioral similarity across several households, several districts, or in a broad range, in that case, the malnutrition in my district may be functionally related to malnutrition in your district. Temperature is also that kind of thing. We say that in Bangalore, the climate is quite good. In the area, very close to Bangalore, the climate is very good. In these particular spaces, places, the climate is very much extreme. In these area, we are getting a lot of humidity. In this area, the weather is very dry. So, all these things result in what will be the crop pattern, etc. And that will have some kind of impact on nutritional status of the children. So things may be interrelated, or there may be certain components which are interrelated, and that is making some kind of interaction for the outcome variable as well. So since there is similarity in the climate, since there is similarity in the culture, therefore the nutritional aspect in your place and my place are similar. Are you agreeing with this matter? Yes or no? Are you not getting me, or what's the problem?
Ma'am, why are you taking a lag?
One question is why I'm taking a lag. Any other question? I think one other student had some question. Would you please ask me? A girl has some question. Okay. Are you not understanding the concept the way I am bringing the lag, or you are raising the question why I am taking a lag? What is your question?
Yes, ma'am. Why we are considering the lag? Why not the current?
Why
In the in the time series, why not both like the neighboring district and the uh, current, like both the districts, why are they not in the same level?
Yeah, they are at the same level. We are using the term lag to indicate, suppose this is a particular area. Here, the term lag is indicating this area has impact on this area, or this area has impact on this area. Okay. So, this is a way we are trying to understand the matter. It's not that they are not at a particular level. Everything is at a particular level. So we are telling about a particular cross section. Okay, so we are talking about 2024. We are talking about today, that is 15th of July. 15th of July, on 15th of July, we are collecting information related to malnutrition in this particular spot. Okay, and we are trying to find out whether any impact of, Bihar, or say UP, or say Odisha, or say some northeast, some state in the northeast, has some connection with the malnutrition in West Bengal. So this is the idea. In context of time series, we consider the same Y variable across time. Here we are considering the same y variable across spaces. And different spaces we are bringing using weight matrix. So I am considering one particular variable. That variable this time is malnutrition. It can be crime. It can be education. It can be anything and everything. So I defined a particular variable and I want to see, while I am discussing the level of education in a particular area, whether that is dependent on level of education in the neighboring area. If I consider crime rate in certain area, whether crime rate in that particular area is a function of crime rates in the neighboring areas or not. So everything is at a particular cross section. We want to check whether Yj has some impact on Yi or not. Okay, to present this matter, while I am writing Wy in the right hand side, keeping some similarity with the time series analysis, we are using the term lag. Okay, getting it?
Yes, ma'am. Got it. Thank you.
Okay, so now to introduce the spatial dependence, I am presenting the equation in this way. So over time, many nitty-gritties will appear in front of us. Since the left-hand side variable is a function of the same variable in the right-hand side, there is some default endogeneity in the system. So I'm not sure how much information do you have on endogeneity. So next day, I'll talk about endogeneity, and for that matter, what can be the best way to estimate the parameters of the model. Will it be least square or it will be something else? So one by one, all these aspects will come in our analysis. How to test whether rho is statistically significant or not. How to check whether in this model there are problems of multicollinearity, whether the analysis of heteroscedasticity, Jerk-Bera statistic, these are important or not. No additional analysis will be done on the basis of autocorrelation because the model itself is autocorrelated. Presence of rho is indicating there is the aspect of autocorrelation. So autocorrelation is already there for basic framing of the model, just like a time series. In a time series model, if I write yt is equal to rho yt minus 1 plus x beta plus error, in that case, I am presenting an autoregressive process. So we don't need to say, this process is autoregressive or error is autoregressive. By default mechanism, it is autoregressive. So here too, as we are writing y is a function of y of the neighboring areas, I am inviting an autoregressive process. So autocorrelation is there by default. So, next day we will try to understand the nitty-gritties, method of estimation, the regression diagnostics, many things are there. Next, I am presenting the spatial error model. So, as I discussed, another aspect of spatial dependency is spatial error model. So, let's see how we can write a spatial error model. So look, it is also possible that omitted variables in a region and their values in the surrounding areas are correlated. you didn't bring several variables as explanatory variables. However, these variables are there in the system. These variables are affecting Y. You could not bring those variables in your analysis. So there are set of omitted variables, and there are set of common omitted variables for your locality, for your neighbor's locality. Okay, so there can be interaction, interconnection between these omitted variables in terms of space, and that may create noise in the standard structure of OLS. In our particular data set, or in our example, awareness of the dietary practices. This is very important to feed your child. However, somehow I could not manage to collect any data, any information on awareness related matters. So this is an important omitted variable. Another important omitted variable can be empowerment or agency of the woman, or better to say, the mother of the child. Whether the mother has sufficient freedom to take decision regarding health related issues of her child or not. Whether the mother is sufficiently educated, whether the mother is in some paid occupation, whether the mother is working in the formal sector, informal sector. So all these aspects create a woman's agency, or sometimes we call it empowerment of the woman. Now, these things may have some kind of spillover or diffusion effect across regions. We generally say that in the western and the southern part of the country, women are more educated, higher percentage is going to the formal sector. Compared to that, in the eastern, in the central, and in the northern part of the country, and and in the northeast part, the percentage of women education is lesser. Lesser of the women of that group is in the formal job market. So statistics is telling that stories. Okay, so we can expect that in certain region, women have better empowerment, better agency, better decision-making power. In the other area, the things are not so. That may be because of the cultural factor, because of the factor that you are not doing these things, therefore I am not doing these things. Okay, so there can be certain kind of spillover effect when we are thinking about why in the eastern zone the girls are lesser educated compared to the southern zone or western part of the country. Okay, so this kind of things are there. Some zonal things are very much there, which we can't deny. So if somehow in our analysis we can't bring these aspects, or we can't collect information on these aspects, the interaction among these factors will make your equation something different from the usual. So we can present the equation in that context as y is equal to x beta, as we presented earlier. Then plus we add the random error, this v component here. Apart from this v, we are also writing another term, lambda wu. This wu, this is the spatially lagged term for original regression error. Original regression error is v. For v, we are adding some additional things, wu. your error, my error are interrelated. So that thing we are presenting here. And while we are presenting this WU, that should come with some associated coefficients which has been presented as lambda. So lambda is the associated coefficient for spatially lagged term. So we are calling idiocentric error. WU, we are considering the lagged error. Lagged does not indicate, different levels. Lag here we are considering in terms of space. Same omitted variables are there in our model, and therefore there is certain kind of interactions in the error term that we are trying to tell in this context. That can be captured when we are writing the model in this form. Y is equal to x beta plus lambda W plus V. V is the usual random error. We call it idiocentric error, and it will follow all the regularity conditions as I discussed in the first slide. Okay. However, I hope you are understanding if we bring WY with certain coefficient as we wrote in the first model, or if we bring WU as we have presented in the second model, the model framework is changing, and maybe the application of least squared will result in biased estimators and biased standard errors of the estimated coefficients. So we have to understand much more things related to this model so that we can suggest this will be the estimation technique, etc. We will more or less, at the end of today's discussion, before closing the thing, I am presenting two other types of models. One is the SARMA model. The first model is the spatially autoregressive model. So we call it SAR, S-A-R, spatially autoregressive framework. This kind of model we call spatially moving average model, MA, moving average model. If there is interconnection among the errors, we call it MA, moving average model. And if we have both, both spatial lag in terms of Y as well as spatial lag in terms of error, we call it spatially autoregressive moving average model, the short form of which is SARMA, SARMA. Both the things may be there. Separately, I talked about spatial lags and spatial error, but both the things can be there. It may happen that xj is affecting xi and thereby affecting yi, or thereby yj is affecting yi. So this is one possibility. Another possibility is we left several explanatory variables, and among these omitted variables, there is an interconnection, there is some spillover effect. And for that matter, there can be spatial error as well. Okay, so if I combine both the spatial lag and spatial error, the equation will look like this. Okay. Another complicated model can be here. Explicitly, we are allowing lag in terms of y, dependent variable, and allowing lag in terms of error. However, there can be lag in terms of x as well. Okay, x in a particular location I can be interrelated with x's in a broad locality. So that interconnection we didn't capture in the first equation written here. That interconnection among the x's can be captured if I consider wx for all explanatory variables along with the coefficient eta. So if this is the framework, we call it the Durbin model. So in our due course, I will discuss about these 4 varieties, the spatial lag model, spatial error model, more complex models like Sarma and Darwin model. Okay. So today I'll stop here, because if I go for some kind of use of software, I need to talk something about the test statistic related to rho or test statistic related to lambda. Only after discussing these things, we can go for, the regression based analysis, where along with the standard OLS matters, which, or the ML matters, here you will get both the information simultaneously, that is R square, adjusted R square. Then you will get, some information related to the ML model as well. So you will get F statistic. Again, you are getting Akaike information, SWOT, criterion, etc. So many things you will get simultaneously if you use the software like Geodaspace. Coefficient values, etc. will be there. And there will be information related to multicollinearity, normality, heteroscedasticity. Also, there will be, diagnostics for spatial dependence test, where Lagrange multiplier test for the lag, robust Lagrange multiplier test for the lag, Lagrange multiplier for the error, robust LM statistic for the error, Lagrange multiplier for the SARMA, where there is both the spatial lag and the spatial error. All this information is coming. So we touched these parts, how to check multicollinearity, how to check normality, how to check heteroscedasticity. But before coming to the software part, we also need to learn about these statistics. And only after this, we will be able to start using the softwares and analyzing the context. Okay? So this is only the snapshot of what we are going to do in the next class. Any question, anybody? I'm quickly taking the attendance. Ovinanda?